Excuse me. Okay, well, we're at 2:02. Why don't we go ahead and get started? So what I was going to be doing today is, if you recall at the end of the last lecture, I somewhat informally posed a hands-on example. The idea was to do some population simulation similar to what I had done for the other ADAS-COG example, but to do it for you guys to do it in the case of the ADAS-COG model that you implemented, where you were just looking at donepezil and placebo. So the idea is make use of that model and then do some simulations that might be suitable for making some inferences about the comparisons between donepezil and placebo, given that information. And so I went ahead and put together some simulations that illustrate doing that. And you'll find you should have gotten an email announcing that I posted a possible solution to doing that. So I'm just showing that here with the course website. So you'll find that with this ADAS-COG sim hands-on.zip. So just unzip that, and that'll create a folder called ADAS-COG sim hands-on that you can put right at the top of your MI260 folder in your flash drive there, and it should be runnable from there. So that's there. And so that's what we're going to go through. But another thing I should mention is I'm way overdue to assign a midterm exam. And I'm going to do my best to get that posted by the end of the week. And what this will be is it's not going to be a real humongous one. For the midterm, what I typically do is just a multiple choice exam, just trying to catch on some of the specific concepts that we've done through here. There might be some relatively simple problems where it's reasonable to do the answer in terms of multiple choice. So I will be posting that fairly soon and announcing it via the course website, and as well as and you'll get the emails from that announcement. I'll just leave it at that. I'll figure out the specific format when we get there, but generally the way it's set up is you actually sort of fill in the answer sheet from the course website, and some instructions will be provided. The other thing I need to do, which I'll either have Jonathan do this coming Wednesday, or maybe I'll just send out the information in the form of an announcement via the website, is to provide you with some information on the criteria for doing the course project. Again, these are things if you're taking the course for credit. So I'll send that out too. So anyway, so keep your eyes open, and those will be coming your way. So let's go ahead and jump on into what we're going to be doing today here, doing some simulations based upon the model that was associated with our hands-on problem 5. So here I just put up the slides that show the model structure here. So recall again, we just had a basic additive normally distributed residual variation term on here. Our basic model is one where we have a linear disease progression plus a placebo effect here, and then a drug effect. The placebo effect in this case is just a constant. though that constant can vary with both trial and individual. And then what else we got here? So yep, and then the drug effect is this mix of a exponential dose response component multiplying an Emax style time component here. And then we've got a couple other random effects in here. We've got an intertrial variation component on the maximal drug effect, this E delta. And we've got some intertrial and as well as inter-individual variation on, where do we go here, on the slope associated with the disease progression. And then finally, we've also got some intertrial variation on the residual variance term. So that was the core model that we're working with. What was this here? So, and then this was just the adjustment to make it appropriate for modeling sample stats in here. But what we're going to do is we're going to take this model, do population simulations, much like I illustrated for the other ADAS-COG case. In fact, the way I built the solution was just to take that and modify it to deal with some of the differences in the models between these and the fact that we only have to worry about donepezil now. And in fact, even in the case of placebo, that just trivially becomes the same model, but with the dose equal to 0. So you don't have to do anything particularly special there. Let's go ahead and fire this up here. Let's show you what we got. Okay, why didn't I make it bigger? There we go. Okay, so the usual bookkeeping stuff at the top. I don't think there was anything really new here other than changing the names here. So we've got the name, the model name is the name of the model that was, is the name of the model that was originally fit, and that's also the name of the directory where it's going to find the results of that, because what we're going to be doing here is going out and grabbing the MCMC samples that were generated when you would fit that model as part of the hands-on problem 5. And then the example name is nothing more than the name of the folder that contains this script. So again, I've allowed for possible parallel processing. For the simplified model, frankly, it's not really necessary because it runs pretty quick unless you increase the number of simulated values, which actually you reasonably could here. Let's see if I'm going to run this. I've got to uncomment. You don't need to uncomment this, but I do to make it run on my computer. Actually, I've got some extra stuff. We actually don't need MBT norm here at all because we're not doing any multivariate normal or T. Everything's univariate, so I could have taken that out. Okay, and the basic idea here is we're going to be doing simulations. So again, we're going to be simulating, essentially simulating a whole population for every sample from our posterior distribution, or more correctly, I guess, every MCMC sample in here. And what I've started with is writing a function that will generate that population given a vector of parameter values. And in our case, that vector will actually correspond to a row from our matrix that contains all of the posterior samples. Design is a data frame that contains our independent variables, which in this case, since we're only working with really one drug, just an epizil, we don't even need to specify that. All we need to do is specify dose and time for our design in this case. NSIM is going to be the number of individuals we're going to simulate, because we do have an inter-individual variation component in our model. So we're going to simulate NSIM individuals, and then to calculate our population mean, we take a mean over those NSIM individuals here. And then finally, we've got our intertrial component here, which if I set it equal to true, indicates that the intertrial variation is treated as part of our posterior uncertainty, and that tends to result in somewhat larger, uh, larger credible intervals than if you set it to false, where the population mean actually averages over the intertrial variation too. So it gives you the choice. So the next step is really just to recode our model that we had originally done in BUGS, now in R. So that's all I'm doing here. In fact, much of this I actually ended up creating by cutting and pasting from the BUGS model and copying it from there and pasting it in here, and then you have to do some reformatting to fit the specifics of R. But the basic forms of the functions are often pretty much the same. So I start out with having to incorporate the intertrial and inter-individual variation so that in the end I've got a vector of individual specific parameter values where necessary, or trial specific ones where I need them. So we start out, well, first of all, to deal with that intertrial bit. If you're going to be treating the intertrial variation as part of the posterior uncertainty, then I just set the number of trials I'm going to simulate every time I call this is just going to be 1. And in here, and so I'll just do a single sample from the intertrial variability. But if I'm going to do it where I'm going to average over essentially a population of trials, then I set NT to NSIM, the same as the number of patients that we're going to simulate. And the next steps are just to go ahead and simulate the intertrial variability. Notice that's all I needed to do for my if-else thing here is just set the ends, because otherwise the statements used to generate the values look the same. The only thing that changes is the number of samples it generates. So I get my study-specific value for E placebo, E delta, and alpha. So that's just our, our placebo effect, our maximal drug effect, and our slope. In the case of E delta, that's sort of the final value we're going to be working with because there is no inter-individual variation on that in our model. But for our placebo and alpha term, we also have inter-individuals, so we have to take the E placebo value, for instance here, plug it in there as it becomes the mean for the next step. Same thing for alpha, and generate the values there. So now these become vectors of NSIM values. And then finally we have down here where we really do the business end, where I'm now going to go through and generate our population. And as I do this, I'm going to, in a sense, reuse the same population for all possible design components, for all possible doses and times is the way this is working. So this S-apply thing is just stepping through all the rows in our design matrix, which has all possible times and doses. So it just goes in here, grabs a row out of that, calculates our E-drug component here. Where are we going here? Yep, our E-drug component, and then goes through and, well, inside here it's calculating essentially the predicted ADAS-Cog change from baseline for all of our NSIM subjects, and then it takes a mean over all of those. And it does that over and over again then for all of our doses and times, and finally spits that out at the end. So we'll get, each time it calls this thing, you're going to get a vector of values, one value for each row of the design matrix when it calls it. Okay, this parameter's plot's just there to tell it which essentially which columns of the posterior matrix it actually needs to keep in order to do the calculations. And down here is where I go out and grab that bugs fit object that has our MCMC samples and does a little bit of reformatting of that and just grabbing the subset that we really need. And then we go to work on the simulations. What we've got here is two numbers of iterations. We've got the number of posterior samples here, which I called NSIM. Actually, that's slightly confusing because that's not the same as the NSIM that was specified up in that function that we had there. So this is going to be the number of posterior samples we're going to use. And NPOP is going to be the number of individuals to sample per population. This NPOP now is actually equivalent to the NSIM from that function up there. And they happen to have been set the same, but they don't have to be. I was just picking round numbers as part of this. So you can pretty much pick whatever you want. In fact, if we wanted to, maybe what we can do is instead of picking a subset of our samples, we could pick all of them. So we've already done posterior. So another option here, for example, is I could just say, well, let's just do all of them. So we'll just do we'll just take them all from the, oops, I just did that backwards. Excuse me. I'm confusing issues already. I'm at this one. That's what I get for trying to do programming in front of people here. Okay, so in fact, I'll leave it that way. I forget what we had. I think we had around 3,000 samples in the way we did this, but I won't swear to that. And then I set up my design data frame here, so I just have to say which doses of donepezil I want and which times I'm interested in. Here I just did basically did the donepezil doses 0 up to 10, and for every 0.5, so 0.5, 1, 1.5, and so on. Picked a few sort of representative times, and then created a data frame using the expand grid function here. And then we do the actual simulation inside here, and depending upon whether you specified multiprocess as true or false, it'll either do it using the par apply function from the parallel package, or it'll just use the standard apply function for doing it. The way this one's set up right now is it has intertrial equals true, which will create the somewhat fatter distributions. I haven't tried it with false with this example. Why don't we do that, because we've already got the result for the true. So why don't I go ahead and set it to false just for the heck of it. In fact, as long as we're doing that, let me rename this so that we won't lose it. What was it? It was true. Right? Okay. So that's where it'll do the simulations then. And in fact, why don't we just go ahead and do them? Let's see. I don't think, did I fire up an R? No, I didn't. Okay, let's go ahead and just do that portion of it. Hopefully I didn't break anything on the way. Okay, let's make sure it just is able to grab everything. Okay, looks like it. Didn't seem to have any errors jump out at us. Actually, how many rows do we have in the posterior here? Let's find out. Yeah, it is 3,000. Okay, so we'll just do that and make sure everything's working the way it's supposed to here. Okay, looks like it's grabbing all of our processors there. Okay. And you can see it didn't take terribly long there. It looks like it's finished. Okay, so it looks like it did what it was supposed to do as far as we can tell. Let's go ahead and make some plots here. Now, what I've done is done a few different things here, but this largely mimics what I did for the other ADAS-Cog, but there's a few differences because of the fact that we're no longer comparing to an active treatment. In this case, we're comparing to placebo, which does have some consequences here, but some of the first ones are simple, where first thing I do is I just calculate median and 90% prediction intervals for ADAS-Cog change from baseline for both placebo and for donepezil. And the way I've got this set up is you can see I've got it written as the ADAS here will just represent the ADAS-Cog change from baseline. And I'm plotting that versus dose. In this case, that means donepezil dose, of course. I'm going to do that for, I'm going to have one panel for every time that we included in here. So that's what's going on here. Then this nonsense is going to create our nice shaded, which one is which here? Where am I going? Yeah, this is going to create our nice shaded curves in here showing our 90% credible intervals for our predictions. And then the stuff down here is just it's overlaying the placebo result on that so that you can see how the two compare. Those predictions. In fact, why don't we just go ahead and do this here? Let's open up a graphics file or window, whatever. Okay, so we'll skip the part where it opens the files there, and let's just show you what that looks like. Okay, so we get a picture like this. And so you can see here, actually, did I do that right? Yeah, I did that right. Okay. So you can see that each panel then represents a different time point, and the red curve is showing you our posterior predictions then for our ADAS-Cog change from baseline for donepezil, and the blue the blue shaded portion represents the placebo predictions in here. So, and not surprisingly, since placebo corresponds simply to the zero dose case, if you actually look at the zero dose case here, it exactly matches up with the placebo since it's really synonymous in this case. So you get, a nice visual representation of comparing those two cases. Now, the other thing I did at first and then sort of hit myself over the head afterwards saying that was a silly thing to do, but I'll show you nonetheless, is I said, okay, let's calculate the probability that each one, the donepezil at various doses is better than placebo. Well, I'll show you what it looks like, and you can see just so you can see the calculations here. I'm just do I want to go through these? The main point here is at some point is it's going through the various design elements here. So we're matching up the appropriate times together for the placebo and active treatment arms here. And then for each one of those, it just calculates the fraction of cases where the result for donepezil is less than that for placebo. And that fraction corresponds to an estimate of the probability that donepezil at that dose is superior to placebo, and then plotting those probabilities. And what we get, in a sense, is not a very interesting result. Is basically what's happened here is, of course, the probability that it's superior is exactly 0 when they're equal, and it's exactly 1 at every non-zero donepezil dose. And if you think about the way the model was structured, that is pretty much driven by the model. Because of the way the model is structured. In fact, I added some notes here to that effect after I did this, saying that it's not a very useful calculation because the model has been constrained in such a way that any non-zero dose of donepezil is going to result in a beneficial effect, or at least a beneficial mean effect. And so you end up with a probability of 1 for superiority to placebo at any at any non-zero dose in here. And then I pose the notion that, maybe that raises a question that if let's say, we're back in the time when donepezil was originally being developed, and there would have been uncertainty in whether donepezil does offer a beneficial effect. Maybe we should have used a more skeptical model in this context, skeptical in the sense that it might have allowed for the possibility that not only, one, there might be no beneficial effect, or even a negative effect in here within our range of uncertainty. And one way we could have actually done it with the existing model is simply allowing our E star, or I guess more specifically E star hat, to allow it to take on negative values in addition to positive ones, and that might have produced a somewhat different picture. If you go back and look at the original structure of the model, we used a log normal prior for E star, which pretty much forced it to be non-negative. In fact, it pretty much forces it to be positive. So that makes the conclusion you see here almost a foregone one. Whereas if we had allowed a distribution that would have permitted it to take on negative values, we might have seen a little more uncertainty around the probability of donepezil being superior to placebo. Anyway, so I did that. The other one here is to calculate the difference compared to placebo. And the first part of the code is actually very similar to the probability calculation in terms of the way this sort of loop is done, except instead of a less than sign here, you have a minus. And I'm not doing a summary at this point. I just let it spit out all the values here. So the end result you get isn't a vector anymore. It's a matrix. And then down here, I calculate the fifth, 50th, and 95th percentiles in order to be able to show this difference compared to placebo. So let's go ahead and show what that looks like in this case. Okay, so I show difference relative to placebo, and again, it's always, except when the dose is identically 0, it's always a beneficial effect here. In this case, down is beneficial. And here I had shown, just overlaid a 0 case corresponding to placebo in this instance, just so you could see the magnitude of the effect relative to placebo. So I guess if you simply want to compare to placebo, those are suitable plots. But if you're developing a compound, chances are the question you want to ask is not simply, is it more beneficial than placebo? You may want to know whether the size of that beneficial effect is large enough to warrant, how do I want to put it? Is it in fact large enough to be of any, really clinically meaningful benefit, not just statistically superior? And so you may already have some idea, or clinicians may have some idea what constitutes a clinically meaningful effect size for a drug for a given thing, in this case for Alzheimer's. Here I just posed a rather arbitrary target that I knew that the drug could at least at least approach. In this case, I just set the target at -2. Now, whether that's where it would have been set by the clinicians at the beginning of, say, the donepezil development, I don't know, but you could reset this target to anything you consider appropriate here. So anyway, I just pictured -2, and this is our target 8S difference from placebo that we're going to shoot for. And you can kind of see already where donepezil sits at different doses relative to that. So you can see -2 here. You can see how at some of the earlier weeks, almost none of the doses, well, 4 weeks, you can see, you probably barely hit it at 4 weeks at the highest dose. You do cross over maybe somewhere near 5 milligrams or so at 8 weeks, and so on up here. We get somewhat increased fraction of these simulations that fall below the -2, but we can formalize that calculation. So one of the first things we can do is simply, to view, for viewing purposes, is just change where our reference line goes here. So that's all I did for this first plot here, as this is nothing more than the last plot, but moving the reference point in here by actually putting a marker here where their target is, so that you can already get some idea what might constitute, say, you might want to estimate, well, what's the minimum dose necessary to achieve that particular target at a given point in time in treatment. So that's one way of looking at it. Now we can get even more probabilistic about it and ask what's the probability that the treatment is better than the target difference from placebo. So we can go ahead and calculate. This is nothing more than the calculation we did before for, that I called prob better. The only difference is now, instead of simply asking, is our value less than this pred ref, I'm asking, is the difference, greater than, it's less than because it's negative, but, is our effect size larger than the target? So that's what we're going to calculate here and plot that. And so now we get a picture more like this, and probably a more meaningful sort of bit of information coming from our model about, what's the probability that we can achieve a particular target, and that in turn, since we've plotted this versus dose, we can get some idea what constitutes what might be a minimally acceptable dose, if that is in fact our target, by identifying a dose where our probability of achieving it is relatively high. Of course, we probably want to look at this and how it also look at things like adverse events or whatever other adverse properties the drug may have to see what offsets this in order to pick an optimal dose. But this would be one step along the way there. Let's actually go ahead and I run this so we get this in PDFs here. I'll just go ahead and rerun the whole thing. Because another thing I could have done, which I didn't do here, is I could have also calculated you can calculate the minimum dose of, for each given time point, you could calculate the minimum dose required to achieve the specified target. That ends up having, you get a different value for each posterior sample, so you actually get a posterior distribution for what that minimum target dose is, and you can actually look at that posterior distribution if you like. Okay, that should have generated our, yeah, we generated our folder of plots here. I was just curious to compare this to here we had set the, assuming I did it correctly, we set the, where'd it go? Yeah, we set the intertrial to false, and I ran it before with true, so I wanted to see how they compared. So this is our, where it's false. Let's get rid of this window. And the one where it was true. What I wanted to do. Okay, so you can see some of the differences here. So, where it's false, you can see a narrower bands than we had over here where it's true. Though the population means are essentially the same. It's a little bit harder to spot because it changed the axes boundaries on here. This picture is the same because keep in mind that essentially the calculation comparing the true treatments is done sort of within study, if you like. So when you're doing that, the intertrial variation has no difference, has little or no effect when you're comparing two treatments within the same trial. This is changed from baseline, a difference between donepezil and placebo. Actually still retains some difference here, but nowhere near as striking as it is when you just look at the raw change from baseline. And of course, that's not going to be any different, and these should be pretty comparable. And there's some difference here. You can see the rate at which it finally climbs up to 1 is maybe a little slower here, a little more gradual. So, if you pick any particular point, there may be a little bit of difference here, but the general gist is pretty similar. Trying to think of any other story to tell around this. I think I don't have a whole lot more. Any comments or questions on either on what we've done, or if you perhaps have other thoughts on how you might want to look at the results of this kind of modeling if you were trying to, let's say you were doing something like developing a new compound where there really wasn't a standard of care out there, and how you might want to look at the dose response in making decisions. Okay, so far nothing popping up here. Looks like we're going to have a short lab session today. That's actually as far as I had taken this so far. Just mention again, keep your eyes out for 1 or 2 emails here with information about the midterm and the course project. I'll be shooting to get those out yet sometime this week. And on Wednesday, you won't be hearing from me this Wednesday. Jonathan will be taking over to talk about modeling longitudinal time to event data. Once when he's done with that, I guess I'll come back in and we'll spend a bit of time on perhaps looking at some other approaches to dealing with some statistics other than just means, as well as starting to talk about how might we deal with combining summary and individual data. Okay, well, looks like nothing's coming up here, so I will just go ahead and say goodbye for now and look forward to talking to you again, I guess in about a week and a half, it looks like. So till then, bye for now.